All right, guys, sorry about the delay there. Had some technical difficulties getting set up today. Isabel Pena, you came in as a guest. Is there a reason why? Do you know? You do too, Andreas Papavasilu. Why does it say that you're a guest? Oh, here, I gotta unmute you guys. All right, well, I don't know why.
Thing where you let him in manually?
Yeah, I mean, I know some of you guys are being shunted to the waiting room. That's not my...
No, well then it's because they're signed in on a different account than with the institution. Because if you log out and sign back in with SSO, aka it goes through the institution, you'll be automatically let into these classes because it's a special account that they made for everyone. Basically using their EID and UT account, basically, because it's connected with Zoom.
Ah.
So they have to sign out on their end and sign in using SSO.
All right, well, I will always admit you guys, I'm not checking to see who... I mean, if somebody comes in from another institution for some reason and they say...
And they're going to learn some math.
They're going to, yeah. I mean, there's some idiot... I guess you guys have heard all about the Zoom bombing and so on, but I'm just going to have to trust people not to be idiots. All right, so you guys have any questions you need to ask me? You did not have a homework due last night because I made the current homework due the following Tuesday, so that's the one you should still keep working on. Hey, let me make an additional point. We set up this Piazza thing for you guys, and I have not seen very much activity over there. I do want to encourage you guys to use that. The TAs are going to monitor that periodically, and I will drop in when I can. Plus, if you all get in the habit of using it, then there will be other people that can maybe address the same questions that you're trying to address. So take advantage of it. You may find, since we're going to be doing a new topic today on these transformations, I know that this gets kind of hard for people sometimes. So take advantage of the resources that we're giving you. I guess that's all I'm trying to say. All right.
Oh, I have a question.
Yeah, go ahead.
Question 2 on the homework that's due tonight. I'm having trouble with the bounds or the limits of integration, and I'm screwing it up. So could you help?
Wait. First of all, didn't I move the due date to next week?
Oh wow, yeah, you did. April 15th. Yeah. Okay.
Yeah. All right, but you're asking about the limits of integration?
For question 2.
Let me pull up the question because I don't remember what it is. So we might all have. Oh yeah, we talked about this problem on another day, didn't we? Maybe not. Maybe it was my other class. Yeah, it's a classic problem. This is the one with the intersecting cylinders, and it can be hard if you do it in the wrong way. But actually, let me take a few minutes just to explain it, because I know I've talked about this with some students, and I think in my other class we spent time on it too. So try to get my camera lined up. There we go. Oops. Why does it not pin? There we go. Okay, listen, you are asked to find the volume in that problem. You're asked to find a volume of a three-dimensional shape that's kind of hard for me to draw, and it's hard to visualize as well. What most people seem to get is the fact that you're somehow in the first octant of space, so that your x-coordinate should be positive, your y-coordinate should be positive, and your z-coordinate should be positive. And you notice that I'm drawing this the way that it was given in the problem set, which is not quite the same way that I usually draw it. I usually have my axes drawn with the right-hand rule. This is violating the right-hand rule. But nonetheless, I'll take their illustration, and that makes it easy to draw two circular arcs for this thing. One's a portion of the YZ plane, and the other's a portion of the XZ plane. Those are the disks that you get by intersecting those two planes with the cylinders, the solid cylinders that stretch out along the x-axis in the one case, and in the other case along the y-axis. So those quarter disks make two portions of, oh wait, I'm sorry, sorry? Okay, I think I have the picture drawn wrong. Let me double check this here. Oh, right. I'm sorry. My apologies. I was intersecting two different cylinders from the ones they gave you in the problem. They didn't ask you to do two horizontal cylinders. They had one of them being a vertical cylinder and then the other one being this horizontal cylinder. So let me draw that again. Same axes, the positive ends of the, boy, I have this wrong, don't I? The x-axis, the y-axis, and the z-axis. And this quarter disk was one portion of the boundary. And that quarter disk then forms one of the walls of this figure. I misspoke when I was drawing that picture up there. Another portion that's easy for you to draw is the intersection of the other cylinder with the coordinate planes involved, but I was drawing a second horizontal cylinder. The other cylinder they gave you was the vertical cylinder that goes in the direction of the z-axis. So this arc that I just drew, that's supposed to be on the floor of the xy plane. You have to understand that those are two portions of the surrounding region. They're two of the boundaries of the region that we're trying to compute the volume of. But there's going to be several other portions. Hang on, let me try to get this. Somebody's microphone is not muted, and I'm trying to see. Isabel, I'm going to mute you. All right. There's three other portions, three other boundary segments to the region that you're stuck inside of, the region that you're trying to find the volume of. I need to imagine you guys wandering around inside this region, and that quarter of a disk, that's the left wall, and the other quarter of the disk, that's the floor. Those are two of the 5 boundary portions of this set. You're not going to be able to get your limits of integration unless you can visualize the set, and I want to have you imagine wandering around inside it so you can talk to all the points. If you actually look at the picture that they drew for this problem, let me see if I can share my screen. Share screen like this, like this. There. So do you guys see now that there is the front surface of this is, you can see a rectangle that's bounded by where there's a line here where the first cylinder pierces the XZ plane, and then there's another line where the other cylinder pierces the XZ plane. So that will make another wall, a rectangular wall, that's going to be a third part of the boundary of this set. So let me go back to my picture. There. So that wall, in my picture, that's going to be here. So those are 3 portions of the boundary of the set. The other 2, each of these 3 portions is a part of a plane, so it feels flat. But the other 2 portions are not part of a plane. Instead, they're going to be parts of the cylinder. So the vertical cylinder that gave me this line segment, it gives me a lot of other vertical line segments. This is part of the cylinder, the vertical cylinder in the picture, which consists of vertical lines that are all kind of planted along that circular disc, a circular arc that's on the floor. Together, those vertical line segments will make a 4th wall to the region that you're stuck inside of. And in the same way, the other cylinder, the one that goes from left to right, that cylinder consists of horizontal lines, a portion of which becomes a roof of this figure. So in addition to those 3 flat walls, the 2 quarter discs and the rectangle, there's another wall that's made of a bunch of vertical sticks, and then there's a roof that's made of a bunch of horizontal sticks. you've got to try to find a way to visualize this. And I'm not exactly sure how to help you. I know that my pictures are not that great. And what's worse is these pictures are presented to you on a flat two-dimensional screen. So it's hard to visualize something three-dimensional. But you got to get it if you have any hope of getting the integral, the limits of integration figured out. So here's the way, if you can visualize it, here's the way that you can get then get your limits of integration. First thing that you should do is to ask why this is an integral at all, because that's actually they're just asking you for the volume of this set, the volume of this room that this person is wandering around in. And the way to turn this into an integration problem is just to say, oh, well, you just have to integrate the constant function that's always equal to 1, integrate that over the set S. After all, what would this integral mean? It would mean you're supposed to take the set S, chop it into little bits, measure the size of each one of those little bits times the value of this function somewhere in that little bit. Well, when you multiply by a 1, then nothing interesting happens. No changes take place. But if you back up a second and you say, wait a minute, how do I measure the size of a portion of this room? The size means volume of a portion of the room. When you have a three-dimensional set and you chop it up, the way you're measuring size is by volume. So this turns your volume question into an integration question. You just are integrating the constant function that's always equal to 1 over the set S. That'll calculate the volume of any three-dimensional set. Of course, you want to use Fubini's theorem to calculate this as a succession of three one-dimensional integrals. The same function is written down there, but you're going to integrate with respect to the 3 different variables one at a time, and you can choose the order in which you write the limits of integration. Let me suggest to you that you put z on the inside, and then x and y. Let's see, I think actually for this problem it makes sense to put x on the inside and y on the outside. X in the middle, I mean, and y on the outside. You're free to do them in any order, but I think setting up the limits of integration and then actually calculating the integral will make it easier in this particular order. So I will do my computations from the inside out, but I have to get the limits of integration from the outside in. I'm sorry, I did that totally wrong. I want z on the outside. No, I was right the first time. I'm sorry, there we go. All right, so what are my limits of integration on y? Where do I go to get the least value of the y coordinate? So where should this person go? Now they can walk and jump, right? To get anywhere inside this three-dimensional set. To get your minimal y coordinate, if that's the positive y-axis, you want to walk against that direction. Walk as far this way as you can. The farthest you can go is you'll be stuck at this rectangular wall here. It's actually a square wall. And that's the set of points that are actually on the xz plane. So those are all points that have a y coordinate of 0. So there's your minimal y coordinate. You get your largest y coordinate by going as far along the positive y-axis as you can, and that would take you to this point. Now, to get the coordinates of this point, you need to know 3 things about that point. And if you can get 3 things about it, then you will have 3 equations. So I might observe that that point over there is on the floor, and it's on this left wall, and it's also underneath the roof line. The roof actually touches the floor there at the back end of the room. So the fact that it's on the floor means that it has a z coordinate of 0. The fact that it's on the left wall means that it has an x coordinate of 0. And the fact that it's on the roof surface, that roof is given by this cylinder. This cylinder is the set of points where y squared plus z squared is equal to whatever the radius is. I don't remember what it was in my picture. Hang on. I have a radius of 3. So for my version of the problem, that cylinder is the set of points where y squared plus z squared is equal to 9. So here's 3 equations. that determine the three surfaces that that point is a part of. If you play these three equations off against each other, you can get the three coordinates. Obviously, two of them are listed here, and the third one comes from solving this equation. Then you know that y is equal to 3. When you move inside the square brackets, now you're going to be holding the y-coordinate fixed, and you want to look at the range of values of the x-coordinate. Holding the y-coordinate fixed means that you're going to be only looking in a plane that's perpendicular to the y-axis. So you need to take this three-dimensional room and chop it with a plane that's perpendicular to the y-axis. When you do that, you're going to get just a line segment that's the intersection of your plane with this left wall. You'll have a line segment down below that's the intersection of your plane with the floor. You'll have a line segment on the right as well, because that's the intersection of that plane with this curvy wall to the right. And finally, you'll have a line segment at the top, because that's where this plane, where y is a constant, meets that cylinder, this cylinder here. This cylinder consists of lines that are parallel to the x-axis. And one of those lines will be intersecting your plane. So imagine now this person who's wandering around inside the set looks at just that rectangle. It's bounded by those four lines, and it's easy enough to figure out the equations of those lines. This line was a part of this plane, the YZ plane, and every point in the YZ plane has an x-coordinate of 0. This line segment was part of the floor, and like every point on the floor, all those points have a z-coordinate of 0. This line segment was a part of the cylinder, and all the points on that cylinder have y squared plus z squared equal to 9. Now, mind you, when we intersected with a plane, that's a plane of points where the y-coordinate is constant. So this equation is telling me that some constant plus z squared is equal to 9, and therefore that line can be thought of as the set of points where z is equal to the square root of 9 minus this constant. And in the same way, this fourth edge is the set of points on my plane where y is a constant that happen to be part of the other cylinder. I don't think I ever wrote out the equation of the other cylinder, but it's x squared plus y squared equals to 9. So just as I said for this one, you're telling me that x squared plus some constant adds up to 9. Well, that's the same as telling me that x is equal to this constant. So now you have a picture complete with equations that describes the two-dimensional set that I need to integrate over on these inner two integrals. Just within that rectangle, what are the least and the greatest values of the x-coordinate? The lowest x-coordinate is 0, and the highest x-coordinate is the square root of 9 minus y squared. Then you hold the x-coordinate fixed. Now, holding the x-coordinate fixed means intersecting also with a plane that's perpendicular to the x-axis. So if I drop such a plane in this picture now, then that will intersect all of this with a vertical line where now the x-coordinate has been held constant. And so now I'm down to just a line segment. And within that set, now I need to ask about the least and the greatest values of the z-coordinate. The minimum z-coordinate is at the bottom. The maximum z-coordinate is at the top. And these are the calculations that I've already got for what those z-coordinates are. So to my way of thinking, this is how you would write the volume calculation as an integral, and this is how you would get the limits of integration. Let me point out that a lot of people would do it a little bit differently, but end up in almost the same position. Because after all, how would you begin actually calculating the integrals? We got the limits of integration working from the outside in. Now to calculate the integral will work from the inside out. Inside most, you have to anti-differentiate that function with respect to that variable and plug in those two endpoints. Well, that's easy. The antiderivative of 1 with respect to z is just z. And when you put in those two z coordinates and subtract, here's what you're going to get. This hasn't changed. This hasn't changed. But now on the inside, what I'm going to have is the square root of 9 minus y squared. And that's what you need to integrate with respect to x and to y. This answer that I just got by thinking about this as a three-dimensional integral, you can also get it straight from thinking about the original problem as just a two-dimensional integral if you can visualize it well enough. After all, what we're looking at in this picture is asking somebody for the volume of the region that lies over this quarter disk in the floor and under some surface. And if you can think of that surface as being the graph of a function, then you could say, oh, well, anytime you ask me for the volume of the region that lies under a graph but over a certain portion of the xy plane, then you're just asking me to integrate over that region of the xy plane exactly the function that I was graphing. So you could have jumped straight to this formula. I mean, you still have to figure out these limits of integration on x and y, but you could have skipped the stuff with the z if you could convince yourself from the beginning that exactly the region that we're looking at, this thing that I've called a room that we're walking around in, if you can convince yourself that that room is the region that lies under the graph of exactly this function. And in my experience, some people can see that right away, and other people are confused because of the other cylinder somehow. So if this is an easy jump for you, then you're welcome to start here. And if not, then I would encourage you to go through that as a triple integral problem, because every volume calculation in principle can be started off as a triple integral. And then you just have to use Fubini's theorem or something. By the way, I wrote it out with x now on the inside and y on the outside because I now know that this is an easy integral to do in this order. You're, of course, welcome to do it with these two variables reversed. And for that matter, you could have put z on the outside in the beginning. It's all up to you. But they're not all equally easy to do. This is the order that turns out to be easiest for the computation of this problem. So I don't remember who asked that question in the first place. I'm sorry that the answer gets so long, but it is a hard problem, and I don't mind going through it just so you can see it.
I get it now. I got the right answer. Thank you.
Okay, all right. Let me pick up on this one example because at the end of the day, we realize, oh, yes, you're just integrating something over this quarter disk. And we had issues like that yesterday when we were together. And that's where a lot of people started to say, can you do these things in polar coordinates? For that matter, can you do this integral in polar coordinates? And the answer is yes. And in fact, we discussed last time a little bit of how you have to do that. If you take, let me put some other function in here. Take, I don't care, some random function of a couple of variables, and somebody asks you to integrate this thing over exactly that quarter of a disk. So this was a disk of radius 3, and it's the portion of the disk of radius 3 centered at the origin, the portion that lies in the first quadrant. And they say, please integrate this with respect to area. What I had you do in this integral here is to say, okay, that's fine. We'll just use Fubini's theorem. We will draw the lines where x is a constant and the lines where y is a constant. And those lines partition this quarter disk into a bunch of little pieces, which is exactly what we need to do in an integral calculation. So we'll take the size, the area of each of these little pieces, and we'll multiply each one of them by the value of this function at some point, doesn't matter which point, chosen inside that little piece. Yay. And in fact, it's easy to do that because I know how to get the area of a little piece. When you take the lines where x is a constant, and then the lines where y is a constant, they partition your setup into a bunch of rectangles. And you know how to get the area of a rectangle. That's just going to be the product of its width and its height. So the width is how far apart you've moved the lines of constant x, and the height is the distance between those two lines of constant y. And of course, you do have to figure out the limits of integration, and we just worked through all of that stuff, and it gets kind of complicated because you had some square root stuff over there. Now, last time we started talking about using polar coordinates, and that's fine. It just takes the same idea that Fubini had, but it says, why don't you split this region up instead by drawing the lines where the theta coordinate stays constant, and also drawing the curves where the r coordinate stays constant. Those are circles. And I've drawn, I guess I drew articles 1 and 2 and 3. And that partitions my set up into little pieces, and I can play the exact same game and say, well, I will add up the value of the function inside each one of these pieces, multiplied by the size, the area of one of those pieces. And I can get my limits of integration by just saying, oh, well, yeah, okay, in this figure, my theta coordinate varies as low as 0 and as high as pi over 2. And my r coordinate, if you fix a value of theta, then my r coordinate varies from r equals 0 up to r equals 3. So great. And, oh, well, I see x's and y's. I don't want x's and y's anymore. I'll just replace them with the formulas involving r's and thetas that tell me what x and y really are. Oh, so that'll help me evaluate the function by just knowing the r and theta coordinates of these points. And then, oh yes, I have to multiply by the area of this little chunk. Now that's where life gets hard, because to get the area of this, I mean, this chunk kind of looks like a rectangle. It's fairly close to a rectangle, I guess, at least if the two lines of constant theta are really close together, this will look like a rectangle, and the area of it would be the product of the lengths of the two sides. One of the sides has a length that, that I would just call dr, because it's the distance between the two r coordinates. But unfortunately, if you let theta vary from one constant to another one, you've got a small change in theta, but that doesn't measure the length of this other side of the pseudo rectangle. The length of that little arc turned out to be r times d theta. So you have this extra fudge factor of an r that has to be included. Okay, a lot of students are willing to buy that, and they say, fine, I'll throw in the extra r. That makes this integral very easy to compute now because my limits of integration are constant for both the theta and the r. In other words, if I were to go to the r theta plane and just mark off all the combinations of r's and thetas that I get, I would find myself in a rectangle. Oh, look, I have it already drawn. Here you see a picture of the r theta plane, or at least a portion of it, where the r-axis is at the bottom, the theta axis goes up. And if you give me two numbers like, oh, I don't know, r equals 1 and theta equals pi over 4, well, I can find that combination in the plane. I go 1 unit to the right and pi over 4 units up. There you go. There's the point where r comma theta is equal to 1 comma pi over 4. So now it appears that the combinations of r's and thetas that I have to integrate over are just the combinations that lie in a rectangle. And integrating over a rectangle is easy according to Fubini. According to Fubini, when you integrate over a rectangle, you just get an iteration of two one-dimensional integrals. That's why we gravitate towards polar coordinates in this problem in the first place. But there is this question of why is there an r in there? Okay, I'm going to answer it for polar coordinates, but I'm going to phrase my answer in such a way that it will apply to other coordinate changes too. You see, what you have to know is that I got to put these two pictures together. Here I have a separate copy of R2. This is the I don't know if you can see it, it's too big. This is the r and theta axes. And in this picture, everything is like rectangular. You'll notice that I'm not drawing lines of constant r as being circles anymore. I'm just drawing them as vertical lines because in the Cartesian coordinate system, if you name a coordinate and hold that coordinate fixed, you're looking at a straight line. Same thing with the theta coordinates. They're a bunch of parallel lines. So you have here a copy of R2, You have here a copy of R2 where I'm using X and Y coordinates to keep my positions straight. I'm using X and Y to determine location. Joining these two is a transformation. That means it's a function, capital T. This T is now a function that goes from the copy of R2 that's on the left to the copy of R2 that's on the right. And just so we all are clear on this, you have already a formula for this transformation. Give me two numbers. I will call those numbers R and theta, but it's just a pair of numbers which I can use to determine a location in space. There, a pair of numbers, for example. Give me those two numbers and I will create two other numbers for you. Here's the formulas that I will use. R times the cosine of theta, comma, R times the sine of theta. This is a function now that takes in pairs of numbers and gives you pairs of numbers. It's a function that takes points in the plane and it gives you points in the plane. But it does it in a kind of a funny way. You guys already know that when you look, for example, at all of the points that have an R coordinate of 1, but the theta coordinates steadily increase, you're going to get points in the plane that have their R coordinate is going to be a 1 with gradually increasing thetas. So all of the points on this straight line are mapped to points along this circle. And another straight line will give us points on another circle. And another straight line will be sent to another circle. By contrast, the horizontal lines are the sets of points where the theta coordinate is being held constant, like pi over 4, pi over 2. And all the points on one of those horizontal lines are being sent to points along a ray. These are all the points that have theta equal to pi over 4. These are all the points that have theta equal to pi over 2. So you see, you are moving points around. You take points in the plane on the left, and you move them to points in the plane on the right. It's a little hard sometimes to see those points like physically moving, but in the case of this particular transformation, I can illustrate it for you. Look, you just take the points that are in the rectangle, you make a fan fold, and then you plop them down onto this other copy of R2. Okay, the scale is off a little bit. But conceptually, this is all you're doing with this transformation. You're picking up the points in the plane, you're mushing them together in some way, and you're plopping them down into points on the plane. I mean, I don't have a formula for it, but I can show you a very interesting function, a different function that goes from R2 to R2. Just do this. There. I took each point in the plane and I moved it to another point in the plane. And in the process, I destroyed my little visual aid. Sorry. Now, here's the thing. When we do these computations with integrals, you know that the spirit of an integral says, chop up your region into little bits, measure the value of the function in each one of those little bits, and multiply by the size, in our case, area, of that little bit. Okay, well, this transformation, the polar coordinates transformation, was helping us do part of that. When you needed to split up this quarter disk into little pieces, one way to do it is what I did up here. Just draw a bunch of parallel lines and get rectangles. Another way to do it is to say, go back to this copy of the plane, chop it up into rectangles, and then apply the transformation to each one of these little rectangles and see where it goes. And we know that it'll go into one of these little sectors that are not quite rectangles anymore. They've got curved two circular edges and two non-parallel edges where the straight rays are. It's not rectangles, but it is still a way of partitioning up the set S. And when part of the recipe says, okay, split the set S up into parts and then evaluate the function inside each one of those parts, well, you can do that part of the job in this picture too, to get a choice of a point inside each one of these sectors. All you need to do is to pick a point inside each one of these rectangles and follow where the point goes, and then evaluate the function there. Oh, but wait, if you need to evaluate this function at that point, and that point is the output from this point in this copy of the plane, then really you could have just evaluated the function right here. Don't use the R and theta coordinates and multiply those together and multiply by 3, but do what the recipe says. take the r and theta coordinates, use these formulas to calculate the x and y coordinates, and then multiply those two things together and multiply that by 3. In other words, you can evaluate the function on the graph paper instead of on this piece of paper by just taking a point, figuring out what its r and theta coordinates are, and then taking 3 times, well, all of this. That much is will be the x coordinate, and that much will be the y coordinate. So after a while, you realize, hey, this is pretty easy. Instead of having to integrate over a disk, the disk, or the quarter disk, that quarter disk is what you get from this transformation by starting off with just a rectangle. So break the rectangle up into little rectangles. Choose a point in each little rectangle. Evaluate the function at each one of those points. Figure out your limits of integration just here in the rectangle. Oh, it's so easy. Rectangle, rectangle, rectangle. Oh, and then I have to multiply by the area of this part. And unfortunately, the area of this little region is not the same as the area of the corresponding region in the previous picture. The areas get shifted. They get stretched or shrunk, and you can see that certainly when you think about how the fan works. When you try to fold a fan up, you see that I'm squishing things near the origin. Clearly, any circle, if I look at, any region, it doesn't matter what the shape is. If you look at a rectangle right here that seems to have a fairly large area, as soon as I apply this transformation, the polar coordinates transformation to it, look, you can see that it's shrinking into something that's much smaller. It still occupies a little bit of space. It's still measuring just as far from left to right, but the up and down, or the twisty part of it, it's not nearly as much as it was before. So areas are being shrunk. The areas of regions that are near the vertical axis, these parts get shrunk in this picture. By contrast, and actually the ones that are over here, a region in this area actually gets stretched when you try to figure out what it looks like on this side. That maybe it's not clear that it's getting stretched, but I'll show you in a second, because there is a theorem that tells us exactly how much stretching or shrinking there is when you apply these transformations. So this is an important theorem. If you're near any point P in the plane, and you look at a region that surrounds the point P, the areas of regions near P will be stretched or shrunk by a factor of, and here's the magic formula, you take the transformation function t, compute its derivative. Okay, so we've talked about differentiating functions that go from like Rn into Rk. Remember, those were k by n matrices. In our case, we have a transformation that goes from R2 to R2, so that's a 2 by 2 matrix, and in particular, it's a square matrix. So since it's a square matrix, I mean, when you evaluate it at the point P, you get a matrix filled with numbers. It's a 2 by 2 matrix, so it therefore has a determinant. And the determinant is the fudge factor that tells you how much areas get stretched or shrunk. More precisely, since areas are supposed to always be positive, I need to take the absolute value of that determinant. So that's the theorem. It's a very important theorem. And to really understand it, it helps to take a linear algebra class, because what we've talked about as the definition of a derivative, remember the derivative of t at a point P, my definition of it weeks ago was that that's the best linear approximation to the original function. It's a linear function that approximates capital T really well near P. So using that idea, you realize all I'm talking about is, yeah, if you had a linear function, how much would that linear function change areas? And you learn in a linear algebra class that that's exactly what the determinant measures. It's the determinant is the determinant of a linear map is the fudge factor that tells you how much areas are being stretched or shrunk. Let me show you this theorem in action. As I said before, if you wanted to compute an integral over this quarter disk, do everything in polar coordinates, and it's all about the rectangles, except for the fact that a rectangle in this region will not be sent to a rectangle over here. In fact, whatever this rectangle is, it'll have an area that's easy to compute, width times height. But the area of this one will be bigger or smaller than that by exactly a factor of this. So let's compute what this is in the polar coordinates setting. So this is the example where we're using t of r comma theta to be the function with two outputs, r cosine of theta and r sine of theta. You may remember that I hope you remember that when you compute the derivative of such a function at any point, since it's a function into R2, you will get two rows from the two gradients, the two derivatives of those two component functions, one row for each component function. And when I talk about gradients, you remember that that means the sequence of partial derivatives. So let me compute those. I will take this first function and compute its partial derivatives first with respect to r, and then with respect to theta. And likewise in the second row, you've got to do it in the same order. First take the derivative with respect to r, and then with respect to theta. And you notice that, as I said, you will get a 2 by 2 matrix. That matrix now has a determinant. And remember, the determinant of a 2 by 2 matrix is found by multiplying those two numbers and then subtracting the product of those two numbers. So that'll be cosine of theta times r cosine of theta minus sine of theta times negative r sine of theta. And now I think you can see that the minus signs will cancel. You'll be able to factor out r. All that you will have left will be some trigonometric stuff, but since sine squared plus cosine squared adds up to 1, this is all you get for the determinant. It's just an r. And you notice that in my picture, the r coordinates, they went from 0 to 3, so all of the r coordinates are positive, so I don't even need to put in the absolute value signs. I just use r. That now is the fudge factor that tells me how much areas are stretched or shrunk when I apply this transformation. And that means that the little area calculation, the thing that we would like to write as a dx dy, well, you can get it by looking at the area of a little piece of this graph paper. That's found by measuring how wide it is and how tall it is. But then you need to multiply by the fudge factor, because the transformation is going to reduce or increase its area according to whether or not it's an area that's near the left, where r is close to 0, and if r is small, then areas will be shrunk, versus areas that are off to the right. When the r coordinate is large, we go as high as r equals 3 here. When the r coordinate is large, every one of these little regions will be transformed in this picture into a region whose area is 3 times bigger, because r goes up as high as 3. So this is why that extra little factor of an r shows up when you do things in polar coordinates. It's not just something to memorize. And yes, I know I tried to explain it by trying to figure out the area of this little piece, and we talked about the length of this arc. And for polar coordinates by themselves, that's fine. But when we start to use other coordinate systems, we do need to know how to get the replacement of that fudge factor. All right, I would like to do a different example where it doesn't use polar coordinates, but it uses a different transformation. You guys want to ask me something about this example before I leave it? No? All right, let me show you this next one. Oops, got some junk from another class there. So here's a new example. Suppose that I ask you to compute an integral of exactly the same function that we just had. But I'm going to give you a different region of integration now. I want you to integrate over the following diamond, so I'll call it D. So let me tell you exactly what diamond I have in mind. I want you to look at the region that's between the lines where x plus y is equal to 1 and the line where x plus y is equal to -1. Those are two parallel lines, slope of -1. And here's a couple of lines with a slope of 1. Here's where y minus x is equal to -1, and this is where y minus x is equal to +1. So that's a diamond. And go, figure out the integral. Now, I hope you are inclined to use Fubini's theorem. I hope you realize that you could get this as an integral. Let's put x on the inside and y on the outside, not that it matters. Anybody know my least and the greatest values of y anywhere inside this set? What's my least y coordinate anywhere inside the diamond? -1, yeah, somebody wrote in -1, Nathan. You should be saying to yourself, you get your minimum y coordinate by going as far to the south as you can. I can see the point. How do I know what point that is? Well, it's the intersection of these two lines. Well, if it's on both of those lines, that means it satisfies both of these equations. Now you got two equations. Use those two equations to figure out the two coordinates. And it turns out the two coordinates are x equals 0, y equals -1. And in the same way, your maximum y coordinate is a 1. Now, what you're going to do for the inner limit of integration? What's your minimum x coordinate? Yeah, silence, huh? Please do not say -1. -1 would be the smallest x coordinate that you can find anywhere within the whole diamond. But when we're doing this inner limit of integration, you're only supposed to be looking at the set of points where y has been held constant. And if you hold y constant, you can only go until you crash into that line. And on the other direction, you can only go till you get to this line. So your x coordinate at its maximum will be the x coordinate of this point, and the x coordinate of this point is 1 minus y. And likewise, the x coordinate of this point turns out to be y minus 1. But there's a catch. This calculation is only valid if I draw that horizontal line in the top half of the figure. If I draw it in the bottom half of the figure, then I have to use those two equations instead to get the two limits of integration. So you really need to compute this integral instead as being the integral over the top half plus the integral over the bottom half. And in each one of those two things, you can do a similar but separate calculation. So the things that I just did up here can be used for this top half, and down here we'll have to do something different. Here's where the change of variable theorem comes in. I'm going to introduce two new coordinates, not r and theta, not x and y. I'm going to call them u and v. And if you ask me what u and v measures, I'm going to say u is whatever x plus y adds up to, and v is whatever x minus y adds up to. Because x plus y is a constant value here and a different constant value here, and come to think of it, it holds other constant values all the way through here. And likewise with the v coordinate. These are the lines where v is being held constant. This diamond consists of all the points where the u coordinate is between -1 and 1, and the v coordinate is also between -1 and 1. So in uv space, I'm just looking at a square. It's not a diamond anymore. Your possible combinations of u's and v's are that independently the u and v could just vary from -1 to +1. See, that'll be an easier region to integrate over. What I need to do now is to find the function that transforms this square into this diamond. And it's not quite a rotation, but almost. There's a little rotation and a little shrinking involved. If u is equal to x plus y and v is equal to y minus x, then when you add these two equations and divide by 2, you'll discover that y is equal to u plus v over 2. And if you subtract and then divide by 2, you'll discover that x is equal to u minus v over 2. Those two formulas right there, they spit out x and y as functions of u and v. That's what this transformation is. Okay, so I know I've gone over, so I probably better stop here, but let's pick up with this next time. I'm going to use exactly this transformation. I gave you the formulas for it. I'll use that transformation to calculate that integral. over this diamond, but I'll be doing it in the new coordinate system. I'll take advantage of that change of variable theorem, and you'll see I'll have to compute the determinant of t prime in the process. All right, I know I ran over, but still I want to ask. So you guys have a question that you want me to answer before we go? Anything about this second example that you want me to answer right away?
Okay, can you re-explain the top half and the bottom half bit?
Yes, I figured you better split this diamond into two parts because everything that I did here is perfect to get the limits of integration as long as I hold y equal to some constant value that's more than 0. If I'm in the top half of the picture, then my least and greatest x coordinates clearly occur along this line and that line. But on the bottom half of the picture, when I hold y equal to some constant negative value, my minimum and maximum x coordinates will be the ones of these 2 points, which are points that are along this line and that line. Those are different equations from those 2 equations. So I'll have to get different limits of integration on the bottom half. It's an annoyance, but it's the only way that you can use Fubini's theorem in Cartesian coordinates with this diamond-shaped figure. And Yangzhu, you were asking a question as well?
Yes, I just want to make sure that the determinant of the linear transformation is from the current coordinates to the xy standard coordinates, right?
That's correct. You need to have the transformation that goes from the u and v, or r and theta, or whatever, the ones that go into the xy space. And I'm glad you asked because that's a common error. A lot of students are accidentally using the one that goes backwards. That would be the inverse transformation. In other words, a lot of students find themselves using this formula. That's wrong. Don't start differentiating this. This also gives a function from the plane to the plane, but it's the backwards one. We want the one that goes in the forward direction.
I was gonna ask about that because like I remember doing something similar a long time ago, but I still don't understand why you're transforming something new into the xy and not transforming the xy into something new.
Well, but see, that's why I did it in polar coordinates first.
I don't know why you went backwards with that either. Or to me, it seemed backwards. Why would you not want to transform xy into r theta to make it doable, not r theta into xy?
Well, I mean, conceptually, you could go either way. But in terms of the calculations, what I need to say is, oh, hey, look, I'm ready to start doing my calculations in polar coordinates, say. And if I'm going to use polar coordinates, I'm taking this picture of r theta space and splitting it up into regions where the theta varies, the thetas are between 2 constant values and the r's are between 2 constant values. In this picture, it's very easy to compute the areas of the pieces because it's just that width times that length, that height. But these are the areas that are going to get transformed to make the picture that I had before, which I've already lost. I don't know where my picture went. This picture here.
But you're starting with an initial xy. You get r and theta based off of that, don't you?
I'm not sure how to answer your question. I mean, the problem was given to us in Cartesian coordinates. Somebody wanted us to take this picture, which literally is a disk, a quarter of a disk, and they want us to take a quarter of a disk and chop it up and ask about the areas of the pieces of the quarter of a disk.
So then why don't you transform that into the r and theta?
Well, you can, but then the question is, okay, if I take this funny shaped region of the quarter disk and I transform it the way you want me to so that I get a rectangle, well, that's great. And now I can calculate the area of this rectangle, but then how do I go back and get the answer for how to get the area of this thing? I don't have my theorem stated in quite the right way. Here, this theorem talks about how much a transformation changes areas. So if you want to talk about a transformation that goes from this picture to that picture, that's fine. You may.
But you need the XY picture in order to create an R theta picture. You can't just start with an R theta picture and then... I'm not really sure what you're doing. Are you starting with an R theta picture and morphing it into what we have as our disk? Or are you starting with the quarter disk and making an R theta grid based off of that?
I'm not sure how to answer your question. I mean, when we did pretty much this example on last time, I think everybody pretty happily just said, oh yes, I see theta varies from 0 to pi over 2 and r varies from 0 to 1. So without having to invoke the language of transformations, I think everyone just understood that you have a correspondence between this collection of combinations of x's and y's and this kind of combination of r's and thetas. I'm not sure that
You're
you necessarily
creating your r theta based off of our xy stuff.
you look at the picture in the xy plane and you determine the picture in the r theta plane. That's true, but there's a correspondence that goes back and forth. I mean, you can talk about, just as in the one that he was asking about a second ago, you can talk about going the other way. There's transformations that go in both directions.
Like if you want everything in terms of r theta, it only makes sense that you transform x and y into r theta.
Okay, let me tell you, I'll tell you what, just to satisfy you, if this works better, if you like this better, you can say it this way, use exactly the theorem that I had before, and then what you're going to need to do is to say that in order to calculate the area, the thing that you have previously wanted to write as dx dy, you're going to have to take, no, I'm sorry. If you want to do the transformation in your direction, then you're going to have to say that the area that determines, the formula that determines how to get areas in the r theta space is you're going to have to take the areas in xy space and multiply, and divide them by the determinant of the transformation that you're using. I want to use a different letter from T. W, how's that? Okay, so now here's the theorem, and this is for people like you who want to go in this direction. That's fine. You have the transformation going this way that takes you into r theta space. You can transform it in the way that you've just decided, but then what you're going to have to do is say, oh, well, the areas in this picture, they're getting divided by the determinant of this one to get the areas on this side. So is that better? I mean, do you want to be talking about dividing by a determinant? I'm not sure.
I literally physically do not understand why you're going from nothing into r xy that's known rather than starting from r xy that's known into r theta. Like, I don't understand how, like, you're starting with the base of xy and you're creating some r theta plot based off of that, but then you're going from r theta that we made back into the xy. Transform that quarter disk into rectangles, and then you're saying you're going to turn those rectangles back into the quarter disk using that T transformation.
Yes. I mean, you can go both ways. You can do it your way. The formula is just going to be harder. I'm not sure why you're pressing.
But how can you transform it back into xy if we're not doing the integrals in xy?
I don't understand your question, really. Suppose that I just have two numbers, a and b, and I say a is equal to b plus 1. So I'm transforming a b into an a. I can also say b is equal to a minus 1, so I transformed an a into a b. I don't understand why you're asking why I'm allowed to do one and not the other. I'm saying you can do them both. So how is that really any different from saying that you have a picture here that can be transformed into this picture, or you can go the other way? I mean, they both exist at the same time.
Because we're starting with this disk. We're not starting with the r theta rectangle. We're starting with the
You are correct. You are correct.
So we have to transform that quarter disk into r theta to make
in such a way that when you transform it the other way, it turns into this one. Yes, sure.
But it's in terms of r theta, so why are you transforming it back into xy?
Think about this as being the double check to make sure that you've chosen the right region here. I mean, realistically, the reason that I don't talk about your transformation is that it makes the formulas look horrible. I mean, realistically, how do you transform a combination? How do you transform a point with x and y coordinates into a point with r and theta coordinates? To get the r and the theta, the r is not so bad. But then the theta is an arctangent. I mean, nobody really likes this. And so if that's your transformation, capital W, have at it. But you're going to have to...
That allows us to do the integral in r and theta, though.
Okay, fine. Use it. You may. Go ahead.
But That's the only way we're allowed to use r and theta, though. That's the
No,
reason
I'm giving you permission
r
to
and
use
theta in
r
our
and theta.
integral.
Why do you think you're not allowed to use the formulas that I had earlier? R cosine of theta, R sine of theta.
Because you brought it back into xy. So
Okay, wait, you know what?
R theta.
Okay, look. First of all, we've reached 1 o'clock, so I'm going to officially end this meeting. At 1 o'clock, I have an office hour. I'm going to turn that one on as soon as this one is over, okay? But I'm going to end this one so that we can release everybody, and then I'll end the recording, okay? If you want to continue this, I'm going to turn on my office hour meeting in just a moment.